Hello everyone, this is Professor Pawan, and in this video we are going to solve the problem based on bending stresses in beams, bending stresses and shear stresses in beams. Okay, now it says there's a beam of I section with 200 mm into 300 mm dimensions, and it has got a web thickness of 10 mm, and this is the web thickness, and the flange thickness of 10 mm, which is this. It carries a shearing force of 10 kilonewton at a section, and what we need to do here is sketch the shear stress distribution across the section. So this is what the problem is. So first thing first, I've drawn the diagram of this I section beam based on the problem, what it looks like. And not just that, I also have drawn one neutral axis which passes through it. Now the first thing I need to do here is I need to locate the neutral axis, and as you're seeing that this beam is basically symmetrical about the horizontal as well as vertical axis. So we know that the neutral axis from the top layer will be exactly in the middle. That is, I'll just write it here. Neutral axis from top layer, I'll denote it as y. It will be equal to this whole distance divided by 2, that is 300 divided by 2, which is 150 mm. Okay, now that we have located the neutral axis, I know that this distance is 150 mm. I'll just write it down. Now I need to find out the moment of inertia for I section, that is the mi of the section, and this also will be about the neutral axis. And since this section is symmetric about both x-axis as well as y-axis, that is horizontal axis as well as vertical axis, the formula to find mi will be quite simple for this I section, which will be equal to bd cube minus small d cube whole divided by 12, where this capital B is equal to 200 mm, capital D is equal to 300 mm. Okay, and then small b is equal to 190 mm and small d is equal to 280 mm. That is this whole d minus this flange portion. Okay, so if I substitute here, I'll just keep substituting here. 200 into 300 cube minus 190 into 280 cube whole divided by 12, and the value here I'll get for I will be equal to 102.427 into 10 raised to 6 mm raised to 4. Okay. So now that we have found out the value of moment of inertia, next thing for us to do will be finding the shear stresses across various critical points in this I section. So I'll just go on finding the shear stress along various critical points in this section. So first I'll write shear stress in the flange. First I'll find out shear stress distribution in the flange portion. Okay. Now we know that shear stress at the top of the flange will be equal to 0. Then we also know that shear stress at the bottom of the flange, it is given by the formula F by I into capital B into a y bar, okay, where y bar is the distance of neutral axis to CG of the flange. Now CG of the flange will be exactly here in the middle of this, that is if this is 10 mm, CG of the flange will be 5 mm from this. So distance from the CG of the flange to the neutral axis, this will be equal to y bar, okay, and what will that be? That will be equal to 150 minus this 10 by 2, which is nothing but 145 mm, okay, and this capital B is the width of the flange, which is 200 mm. Then capital A is the area of the flange, which is 200 into 10, okay, and the thing which is remaining, I is the moment of inertia, area moment of inertia, which we just now found out. So I'll substitute the values here. So this will become force is given as 10 kilonewton, that is 10 into 10 power 3 Newton, divided by the moment of inertia that we found out, which is 102.427 into 10 power 6 into width is 200, and this whole into area is 200 into 10 into this is 145. So this thing, shear stress at the bottom of the flange, the value will get it as 0.1416 Newton per mm square. This is the shear stress at the bottom of the flange, okay. Now we'll try to find out the shear stress at the web, shear stress distribution in the web. I'll write it down here, in the web, okay. Now first thing we need to do is we need to find out shear stress at the junction. So I'll write down shear stress at junction, that will be equal to the previous value which we found into capital B by small b, that is equal to, previous value is 0.1416 into capital B by small b. Here capital B is the width of the flange, whereas small b is the width of the web. So if I substitute these values, I will get the shear stress at the junction as 2.832 Newton per mm square, okay. So this is the shear stress at the junction, and next we need to find out is the maximum shear stress value which will be at the neutral axis, that is exactly here, and the formula to find that is I'll just write down maximum shear stress at neutral axis. I'll write this down as tau max, and the formula is F divided by I into small b into a y bar. Now here again F is the force, shear force which is exerted, that is 10 kilonewton. I is the moment of inertia, B is the width of the web, and here this a y bar whole term is different compared to earlier. Here a y bar means a1 y1 plus a2 y2, where a1 y1 is the area moment of inertia of the flange about the neutral axis, and a2 y2 is the area moment of the web above neutral axis, about neutral axis. So here I'll write it as a y bar is equal to a1 y1 plus a2 y2. As I said earlier, a1 y1 is area moment of moment of area of flange above neutral axis, and a2 y2 is area moment of web above neutral axis, about neutral axis, okay. So this will be finding out, this will be equal to 200 into 10 into 145, this is a1 y1, in plus a2 y2 is 10 into 140 into 140 divided by 2. This is A2 Y2. So this whole term, it becomes 388,000 mm cube. So this is A y bar. And now if I substitute all the values in this, if I substitute all the values in this formula, I'll get tau max value as 3.788 Newton per mm square. This is the value that we will get. Okay. So once we get the maximum shear stress value, ultimately only thing that we need to do now is draw the shear force, shear stress distribution throughout this. And how will we do that? First, I will just extend this projection so that I'll be able to draw the shear stress distribution. First, I'll draw the datum line like this. And I'll also extend the portion which belongs to the flange thicknesses. Okay. Now, at the top of the flange, the shear stress will be 0, and at the bottom of the flange, the shear stress value that we calculated, how much is it? At the bottom of the flange, it is 0.1416, and the variation will be parabolic like this. This is 0 and this is 0.1416 Newton per mm square. Now, at the junction of flange and web, what happens is the shear stress, it increases, and from 0.1416 Newton per mm square, it becomes 2.832 Newton per mm square. Okay, and from the junction till neutral axis, it again increases, and at the neutral axis it becomes 3.788 Newton per mm square. Okay, and since this is symmetrical about the horizontal axis, the same values will be continued below the neutral axis. Okay, same values will be continued below the neutral axis like this, and this is how we draw the shear stress distribution diagram for an I section beam. Okay. Thank you guys. We'll solve more problem in the next videos. Thank you.